Hydrates means that you have something that has water in it, okay, and that's water molecules. So for example, you can have a substance like CaSO4, and that might say 5H2O, and there is a dot here. This dot here is in the center. It's not like sitting at the bottom of the line, okay, so it's not like this. 5H2O. It's not like this. It's kind of in the center, okay, and it's a nice big dot. So that's how you write hydrates. What does this really mean, a hydrate? First of all, a hydrate indicates that when the substance solidified or crystallized, it trapped some water in it. Okay, and so in this case, where you have, this is calcium sulfate. Okay, all right, calcium sulfate. So when calcium sulfate crystallized, when it solidified, it also trapped 5 molecules of water. Can it trap 4? Maybe, maybe not. Okay. Usually with these trappings of water or these hydrates that are formed are very specific. Okay. So for example, if you have another compound, maybe it absorbs only 2 molecules of water. Okay. So you can have different kinds of hydrates. So in this case, let's say hypothetically speaking, this has 5 molecules of water. So this water is what we call the hydrate. So the name of this compound will be calcium sulfate. And then this is 5, so that becomes pentahydrate. It's a very simple thing. Okay. So the name of the salt is still the same, the compound is still the same, and then whatever water you have, that's actually called hydrate, not water. And then you use the prefixes that you're aware of, the mono, di, tri, and all that. Okay, you use those for the prefix here for the hydrate. One of the nice things about these hydrates, if you wanted to, you can actually get rid of this. Okay, the 5H2O, you can easily get rid of it. This is something that you're going to be doing in your next lab. I know some of you are still working on separation lab, okay, but next week you're getting to a hydrate lab, all right? And the hydrate lab, what you'll do is you'll take a hydrate and you'll burn the heck out of it completely on the Bunsen burner, and you will remove the water, okay? And so from chapter 3, we're going to learn about how to calculate mass percents, and so you'll calculate the percent, okay, of water that has evaporated while you were heating it, okay? And so you can easily remove the water. A very practical application of this, which you have encountered, okay, you don't think about it, but you have encountered, is if you buy shoes and leather bags and all that, do you see a little packet in there? Remember? Yes, that little packet is actually one of these salts, okay, which can absorb the water, okay, in there. So you leave it in there so that it absorbs the water, okay, eventually over a long period of time. Eventually, of course, it's going to get so hydrated that you can't use it anymore, okay, because it's completely saturated with water. So until that time, you can still use it. So a lot of these goods that you get, okay, they will all have this little packet in them, okay? Don't eat. Of course not. Okay, all right. Yeah.
Would salt water be considered a hydrate?
No, when you have a solution, then it's not a hydrate.
Okay.
Okay, a hydrate is usually something that is solid. And when it's usually a solid. So even though you have hydrates like these ones, these are usually solids. So the only time it will start becoming a liquid or a solution would be when it's completely saturated with water. So for example, sometimes, and this happens when you have really high humidity, you might have noticed this, the salt starts turning into a solution, right? If you have really high humidity and you leave the salt outside, like these days, if you leave the salt shaker outside, you will never have salt in there, right? You will have a salt solution in there, okay? It will start to get hard and all that. So that is a salt solution, it's not a hydrate, okay? Yeah. Hydrate is particularly where you have, say, if you have a crystal structure like this, so nice that we have all these things in here. So if you have something like this as a crystal structure, then you will have water trapped inside here. That's really what hydrate means, okay? So it's still a solid, it is not going to be a solution. Okay. All right, and then we get into another category which are called acids, and we'll talk about bases also. Acids are something that contain hydrogen ions, and hydrogen ions are H+. So hydrogen group number 1. Okay, group number 1 hydrogen is really weird, all right? Because when you have hydrogen in group number 1 as well as in 7, it tells you two things. In group number 1, as you know, alkali metals like to give 1 electron away. Okay, we learned that already in the last lecture. So if it gives 1 electron away, which means that hydrogen, which is 1,1, is 1 electron, 1 proton, minus 1 electron, so 0 electrons now, and it has still the 1 proton. Okay, so it can do this, which is give the electron away. On the other hand, hydrogen can also accept 1 electron, which is why it's in group number 7, and it still has the 1 proton, so which means now it has 2 electrons and 1 proton. So here it is 1 negative, okay, 1 extra electron, and here it is 1 proton, so 1 positive, and this is 1 negative. Okay, over here. This was called the, H minus 1 is called the hydride. Okay, that's what we talked about. Because if you use hydrogen as a typical non-metal, it's called the hydride. Okay, the hydrogen as a positive. Okay, so for this hydrogen over here that I've written, this would be H plus. In this case, this is the ion I'm talking about here in acids. Okay, the H plus ion. So hydrogen ions. And hydrogen ions over here, since they've given their electron away, the only particle that's remaining in there is a proton, right? There's only a proton remaining. So sometimes you also end up calling this a proton. So sometimes you don't call it a hydrogen ion, you just say that an acid is something that contains protons because it is just H plus. Okay, and H plus means that you only have 1 particle in it, which is the proton. Okay, so first of all, you can have different kinds of acids. We'll do binary acids first, and binary means 2. Okay, diatomic also meant 2. Binary also means 2, just different ways of indicating 2. Binary acids are the ones that you get with halogens. So HF, HCl, HBr, and then HI. If I were to give you these compounds to name, without telling you that they were acids, the HCl, you would call that hydrogen chloride, right? Okay, we call hydrogen chloride. Acids are not like that, okay? Acids are all made in water, okay? That's the key thing about it, and that's how you differentiate between the two. So make a note over here. Acids are made in water, always, always. If something is not in water, okay, with what I'm writing on the board right now, then they're not considered to be acids. So HCl by itself is hydrogen chloride. It is not considered to be an acid. It is just hydrogen chloride. That's it, okay? And it's not acidic in nature. However, as soon as I put that in water, suddenly everything changes. So how do you know it's in water, right? I have to tell you that it's in water. So for those, we use simple indicators. We can, let me see if I can get that over here. So G for gas, L for liquid, S for solid, and then we also have AQ for aqueous. And aqueous means something that is dissolved in water. So it's a solution, but very specifically made in water. These 3 states are just the normal states that you know about. Okay, so gas, liquid, solid, that's all fine. But the AQ is the new one, and that is dissolved in water. So here I have to indicate that this is AQ, this is AQ, AQ, and AQ. Please write these as subscripts. Okay, they are not written with the line, they're written as subscripts. Sometimes you can get away with writing it in the line. Okay, it's not like the number symbol, but still, okay, try to write it as subscripts if you are. Okay, so then HF, AQ, suddenly is not hydrogen fluoride anymore. It's going to become hydrofluoric acid. Okay, and here, hydrofluoric acid. So the nice thing is that, of course, that you're ending the name in acid, so you already know it's an acid. Okay, that's the good thing. And how do you know it's an acid? It's because of the AQ. Okay, at least for these binary acids, you need to know that. Okay, the other ones you will not, but for the binary acids, you will need to know this. So hydrofluoric acid, go ahead and help me out here.
Hydrofluoric.
Hydrofluoric acid. Hydrobromic acid. And then hydroiodic acid. These are the 4 acids that come from the halogen group, group number 7. The most common acid over here that you will encounter in your lab is going to be HCl, hydrochloric acid. You do not encounter hydrofluoric, hydrobromic, or hydroiodic acid because all of those are highly corrosive. Okay, they're very dangerous to use, so we don't use them. Okay, and I've seen some of them, I haven't used any of them, but they're highly corrosive and very dangerous to use. Hydrochloric acid is the tamest one, okay, to use. Okay, even though the concentrated one is not that great, but still. Okay, so these are the binary acids, and then we have what are called the oxoacids. Oxoacid, as the name states, it is something that has oxygen, okay, in it. Now this one, you really need to know your polyatomic ions well, okay? So if you want, you can use your cheat sheet, go back to the list that I gave you, because I'm going to pull ions from there, okay? And then I will make the acids from there, because that's the only way you form these oxoacids, okay? So the first ion that I gave you, I think, was carbonate, okay, in there. So carbonate was CO3, 2 minus, okay, if you remember. So here, if I add 2H plus to this, then this will become H2CO3, right? This is simple math, not a chemical equation. So here 2 minus and then the 2H plus, and that gives me H2CO3. H2CO3 is the acid, okay, in there. So all the polyatomic ions that you have learned, if you add protons to those, they become acids. Okay, that's how it works. So let me write the other ones also. Here you have sulfate, 2 minus, and this will become H2SO4. You have NO3 minus, that will become HNO3. Then there is PO4, 3 minus. That will become H3PO4. These are some of the common acids that you will encounter, so I'm writing them. And then there was the C2H3O2 minus. Do you remember this one? Acetate. The weirdest one is the acetate. And this is the acetate. This is HC2H3O2. Okay, few things to notice in all the acids that we write out. First of all, the hydrogen is always written in the front. Okay, so it gives you an idea right away that you're dealing with an acid. Okay, so here also all the hydrogens are written right in the front. Okay, so you know that you're dealing with an acid. Now for the names of these, the names are not exactly like the polyatomic ions. Okay, the polyatomic ion, this is carbonate, this is sulfate, but these are not anything like that. Okay, so the top one here, this is called carbonic acid. Do you know this one?
Sulfuric acid.
Sulfuric acid, very good. So it has nothing to do with sulfate, although it's kind of there, but not really there. The next one is, anyone? HNO3. There's some nit in there, right? Nitric acid. There's some nit in there. So this is nitric acid. This one would be phosphoric acid. And then the last one is acetic acid.
Why the H3 or the hydrogen, the 3 hydrogen ions and the acetate? Is there a way, like, I know you can't add them together because
You can't add them together.
hydrogen, but
No, you can because they're hydrogen. But the thing about the proton that we're talking about, and this is something you will learn in GenChem2, okay, is that this proton is different from this one. Okay, these two hydrogens are not equivalent. Okay, so that's why you write this separately.
That hydrogen wouldn't just bond specifically, or wouldn't just group itself with the other hydrogens.
Here is what it looks like. Okay, and being an organic chemist, it really bothers me a little bit to write it this way. Okay, and I have to because in all Gen Chem textbooks, this is what you will find. Okay, because in general chemistry, you're just getting used to the acids. Okay, but when you get to organic chemistry, then this is how it's written out. CH3COOH. So the proton that we're talking about is this one. So this hydrogen is bonded differently than this hydrogen. Okay, so it's because these two are different, they have different properties. This is the acidic one, these ones are not acidic, okay, at all. So that's why it's written out separately. Okay, and then you will learn about this later on. Okay, so these are the common acids you will encounter, and trust me, you will encounter almost all of them. Carbonic acid you encounter all the time if you're drinking pop, even right now, I know you will encounter carbonic acid. Carbonic acid is also always present in your lungs because you have carbon dioxide there. So you mix carbon dioxide with water and you get carbonic acid, so you always have that equilibrium in your lungs. That's carbonic acid for you. Sulfuric acid you will encounter in lab.
I'm so sorry.
Good song.
That was supposed to
Enjoy.
be on silent.
Okay, all right, so sulfuric acid, you know that you find in your car batteries, correct? Correct, very, very strong acid there. Nitric acid you probably don't find in your general life. You will encounter this in lab though. Okay, there's one lab where we have, where you will use this nitric acid, concentrated one. Phosphoric acid is also something that you drink, which is also found in a lot of the carbonated beverages. Okay, and so that's something you encounter. Vinegar is acetic acid, so yes, you do encounter that all the time as well. So acids are very common in our life. Those ones you will not. The binary acids you will not. Okay, you encounter oxyacids a little bit more. These acids, please, you just have to know them. Okay, there's nothing I can do about this. Okay, so you just have to know the names of all of these. Luckily, you will encounter them in lab also, and so hopefully you'll become familiar as we go. Questions? All right then, bases. These are usually hydroxides. And hydroxides meaning the polyatomic ion hydroxide, OH minus. So these are usually hydroxides, which means any compound that has a hydroxide in it can be considered as a base. Okay, and so for example, even something as this one. What's the name of this?
Ammonia.
Yes, ammonium. Okay, so ammonium hydroxide, and then we can have sodium hydroxide, potassium hydroxide, calcium hydroxide, any hydroxide possible. Potassium hydroxide, calcium hydroxide, and my writing gets better and better. I especially like ammonium because ammonium, all you gotta do is write A, and then you can do whatever you want. There, that's ammonium.
Okay,
Okay, just kidding. All right. There, it's not. Okay. Anyhow, so those are your bases. And by the way, acids and bases, these are categories of compounds, just like hydrates are a category of compounds. Acids and bases have very specific properties, which we'll go over in chapter 4. Okay, not right now, but that's why you have to learn the names of these. Okay, all right. Any questions? Wow, you guys are great. Okay, fine, good then. That covers chapter 2 for us. There is one portion in it, which is section 2.9, which I will do in chapter 3 when we get there. Okay, so right now you can skip it. If you're doing any of the chapter problems from the textbook, which you should be doing, by the way, then skip that portion. Okay, with the equations in there, you will use it later on. Okay, we will do it later.